Here I have a tower, right? Probably an electric tower. It's not really specified. So here's an example. We have a tower. Let me see how to phrase that. Let's say a tower is anchored by a wire. I have a tower. It's anchored by a wire to the ground. Let's say by means of, I'm following. This is the sample problem. This is sample problem number 2.7 from your textbook. So I'm just trying to follow the same problem statement. By means of a bolt, bolt at point A, right? This is the bolt it's talking about, at A. Now the tension in the wire, the tension in the wire is 2500 Newton, right? That's given. Now we're asked to determine A, the components Fx, Fy, and Fz of the force acting on this cable, or on the bolt, where to say, acting on the bolt, and B, we are asked to find the direction angle, or direction angles, direction angles, theta x, theta y, theta z, defining, they gave this extra explanation, defining the direction of the force, defining the direction of the force, So we have cable, connect, one side is connected to support A, the bolt A, the other side is connected to this tower at point B. Obviously the cable is at tension, as we said before. Cables, ropes, chains, threads, they can only handle tension or pulling force. Now, before we get started, remember when we talked about ropes or cables, we said, well, first of all, they always have to be under tension, pulling force. Second of all, the force throughout this cable is constant. So you look at here, look at here, look at here, at any point in this cable, the force is the same. The value of the force is the same. Right? So these two, just always remember when we talk about cables. Now, a little bit of review of the of Newton's third law. So the cable is on tension, right? So meaning that this cable is trying to, think about it this way, it's trying to pull out this bolt. This bolt here at point A, the cable is pulling this bolt. In an extreme version, if the force is too much, it's gonna take the bolt out of its position, and the tower might fall. Now, third law, if you remember, Newton's third law was about action and reaction. So if this cable is trying to pull this bolt out of its place, because the bolt is not coming out of its place and it is at static equilibrium, meaning that the bolt is applying a force in opposite direction, right? And the magnitude of the force is exactly equal to the force that the cable is trying to pull the bolt out. The magnitude is the same, direction is opposite. Remember the third Newton's law. So I put the force on a bolt this way. So this is where the bolt is, and this is the force applied to the bolt. We'll call it F. This is the force we're trying to find. Right. Now, to find this, I'm going to follow what I just said in the previous slide. I have my coordinate system. Let's name these. Let's call this X, call this one Y, and this one Z. And this is the origin of this coordinate system. Always your coordinate system should be right-hand side. So you can play around with these axes and name them differently, but always in this course, and probably for the rest of engineering courses and in career, wherever you go, we always follow the right-hand rule. So meaning that if my four fingers are pointing in X direction, if I go in this direction, better to say, go from, let's say, whatever is this X direction, if I start making a fist, right, this direction should be, well, better to say, my fingers should be bent towards Y direction, and my thumb should represent a Z axis. So in this case, this is X. I start making a fist, right? My fingers are moving towards Y axis, and my thumb shows Z axis. So if you put coordinate system that does not follow this, right? X going to Y representing Z, it's not right hand it's not following the right hand rule. So you have to make sure that this always holds true, just as a reminder. Now, once I put my coordinate system and I know where this force is, the direction of the force, at least on this figure, I can start looking at 2 points on this line, the line of action for this force, like point A and point B. I'm going to follow what I said, right? I need to know the coordinates of these 2 points, so I can find the unit vector along this line and use that to find the vector for this force. Why am I trying to find the vector for the force? Well, because the components of that vector in XYZ coordinate system, or this Cartesian coordinate system, is going to be Fx, Fy, and Fz, which the problem is asking me to find. So at point A, right, let's put here. Well, let's say we have XA, YA, and ZA. And at point B, we have XB, YB, and ZB. Now, what are these components? What are these values? Can someone tell me what is XA, YA, and ZA? Looking at the coordinate system, you have point A here. Now, tell me what is XA, what is YA, and what is ZA for point A.
I got it. It would be 40, 30, 0 for point A.
For point A, you get 40, right, along X, exactly. So this is 40. For Y-axis, you get 30, positive. For Z, it's 0 because point A is in XY plane. Right? So that would be 0, exactly. Now for point B, give me a second, folks. I have to bring up, okay. Now for point B, what do we get for point B?
Would it be 40, 30, 80?
Well, give it another shot. So point B is here, right? Along Z-axis, and pretty much following this line going up. So this is point B. So what would be the X value for point B?
Would it be 0, 0, 80?
Would be 0, 0, 80, right? Because it's just on Z-axis. So when we have a point on Z-axis, obviously X and Y are 0, right? The only thing left is the value of Z, whatever it is, which is 80 meters up. So this is value for A, this is value for B. Knowing these 2 points, we can write the vector from A to B. Remember we said it's xb minus xai plus yb minus yaj plus zb minus zak. So xb minus xa give me minus 40 I in x direction, obviously. YB minus YA gives me minus 30 J. And then we have ZB minus ZA, which is plus 80 K. So I got my vector from A to B, pointing from A to B. Next step was to find the unit vector from this vector. Remember, I'm doing all these to just represent the force because I already know the magnitude of the force. I'm given the magnitude, which is 2,500 newtons. So what I'm trying to do is that to just represent that in the form of a vector. So unit vector A, well, let's not call it A because A is a point here. Just call it unit vector. Would be the vector, whatever the vector R is I got here, divided by the magnitude of vector R. If I want to write everything, would be minus 40I minus 30J plus 80K divided by square root of, we said the magnitude of a vector in three-dimensional is basically just the square root of all the components squared, like summing them up. Right? It would be 40, well, let's put minus squared. Doesn't really matter, minus or plus. Plus minus 30 squared plus 80 squared. You do this math, you will get the unit vector. So the values you're going to get are minus 0.424I minus 0.13J and plus 0.848K. This will be your, go ahead, Sam.
Sorry, quick question. Could you write the R vector just as a vector notation, like -40, -30, and then 80, and then you just divide it by the magnitude, or do you have to write it like I, J, and K like that?
No, you don't. So let me see if I understood it correctly. You're saying that instead of writing it like this way here,
Yeah.
that's what it's trying. You just write it minus 40, 30, and 80. That's what you mean?
Yeah, and like vector notation, so like the other brackets, like the triangular ones. You know what I mean?
I'm a little lost there.
It's okay. I'll just do it like that.
Okay, but it doesn't matter how you represent the vector.
Okay.
You know, as long as you can find the, I'm just putting all the steps here.
Okay.
As long as you just get the value for unit vector, you're good to go.
All right. Thank you.
Of course. Just, you know, guys, if you have something you can type, I can always, let me activate that. I can give you permission to write on the board, enable annotation. So you can actually write on this board from your computer and point at whatever you want to point at. Oh, I see what you're saying. Yeah, you can do that. I don't really use that notation, but that's pretty much the same thing. It's a different way of representing. It's all good. Thank you, Connor. You clear things up, I guess. Okay, so I got unit vector. Now the next step would be just find the force along this direction. Right? I'm gonna do what we do for that. Basically, the magnitude of force times unit vector. Now the magnitude of force I'm given is 2,500 newtons, right? So once I have that value, I can just plug that in. This is 2,500 Newton, right? And from there you can do the math. You can do the calculation. You'll get minus 1060I minus 795J plus 2120K. So from here, we can see Fx is minus 1060 Newton. Fy is, I'm just putting the components separately so it's more clear, Newton. And Fz is 2120 Newton. So we get 3 components. Now, once you have these components, the rest is easier. That's what you were asked in the first part. A was the components Fx, Fy, and Fz of the force acting on the bolt. So that's what we found. Now, the second part is asking us to find the direction angles. Well, once you know the components in each direction and you know the magnitude of the force, you can just go back to what we covered when we were reviewing vectors in 3 dimension. Right? You can just find theta x, the angle it creates, the vector creates with x direction would be cosine fx over the magnitude of f. Theta y would be cosine fy, the magnitude of f. And theta z, remember theta x, theta y, theta z, I introduced them also as alpha, beta, and gamma. Well, they're the same, depending on which textbook you pick up. They might have used either of these notations. So fx is minus 1060 divided by 2500. If you find, well, obviously this should be cosine inverse. Once you find it, do the calculation, divide this, find the inverse of this angle, whatever it is, it gives you, this value is, it gives you 115.09 degrees. The next one gives you 108.54 degrees. And the last one should give you about 32 degrees. There you go. So these are the angles that force has with different axes.